Hello, this is Jack Jackson. In this series of videos, 4.3 of statistics, we've been looking at confidence intervals. Okay, we started talking a little bit about what they are in general. We've talked about normal computation for probabilities, to review that, and then we've looked at how to derive a basic method for what we call a z-interval. And then in the last video, we stepped through very carefully, step by step, an example. So after studying that example, you should be able to do this next example that we're going to cover in this video pretty easily on your own. So I'm going to present this to you as an exercise. So suppose that a hospital is measuring the birth weights of all newborn babies. They've already collected weights from a random sample of 40 babies and computed the mean weight to be 122 ounces. Use this information to construct a 97% confidence interval for the mean weight of all babies from the larger population. Furthermore, suppose that they know that the standard deviation of weights in the population is 15 ounces. Okay, so what I'd like you to do is pause the video here in just a second and work this from all the way through, compute a confidence interval, and then interpret it in the context of the problem. When you think you've got it all worked out, come back and check your results. So it's important that you do this one on your own and then come back and check. Press pause now. Well, okay, you're back. Hopefully you've done this problem. So the first thing we have to do is to see see what technique we're supposed to use. So in this case, notice that we want to construct a confidence interval for a true mean of a larger population. Secondly, the standard deviation of the population is known. It's 15 ounces. And the sample size is greater than 30, so we can be assured that the distribution of sample means is approximated well enough to use these techniques by normal distribution. So with these conditions, these three conditions satisfied, we see that we can use the z-interval technique that we worked through in the last problem. So hopefully that's what you did, and hopefully you checked these three conditions before you jumped in to proceed. All right, here's all the computations. Oops. So let's see what we got. N, the random sample of 40 babies, so N is the sample size is 40. The mean weight of the sample was 122 ounces. So X bar is 122. The standard deviation of the weights in the population is 15 ounces. So the standard deviation of the X's, sigma sub X, is 15. And we're doing a 97% confidence interval, so that's 1 minus alpha is 0.97. We need to find 1 minus alpha over 2. Now the easiest way to do that is just add 1 to the confidence level. So it's just going to change that 0 placeholder into a 1. So it's 1.97 and divide by 2. And you get 0.985. That's the easiest way to get 1 minus alpha over 2. All right, now then you need to know this formula. The margin of error is sigma of x's divided by square root of n times the inverse norm of 1 minus alpha over 2. As I just said, the 1 minus alpha over 2 is 0.985. The 15 is for the sigma, and the 40 is the n. Plug this in your calculator, as you see done here. 15 divided by square root of 40 times inverse norm of 0.985, comma 0, comma 1. Store it as e, or you can leave off the 0, 1 and store it as e, still the same thing. And so I figured out that value of 5.146821635 as our margin of error. And I've stored it as e. And then I went ahead and took the 122 and stored it as m for mean, the x bar, there of 122. Then I just need to compute m minus e in my calculator, there it is, and m plus e, and so those are my lower and upper limits for my confidence interval. And if we round off to something reasonable, like maybe 1 decimal place, this would be 116.9 ounces up to 127.1 ounces. Now, let's interpret this in the context of the problem. So the 97% confidence interval from the mean weight of all babies is 116.9 ounces up to 127.1 ounces. So we are 97% sure that the true mean is in this interval. So in other words, if we were to repeat this process with different samples of 40 baby weights, we would expect this process to produce different confidence intervals of the same width, which capture the true mean about 97% of the time. So about 97% of intervals computed this way will actually contain the true mean.